A few weeks ago, a headline started spreading across social media that sounded almost too strange to be true. It claimed that IBM's quantum computer, sitting more than 4,000 miles away from Google's lab, had somehow detected the exact same signal that Google's Willow chip had picked up. Some versions of the story went even further, suggesting that Willow had brushed against something from a parallel universe, and that IBM's machine had echoed it back from across an ocean. Videos racked up millions of views, comment sections filled with people asking if we had just stumbled onto proof of alternate realities. And for a moment, it felt like science fiction had quietly become science fact. But before you get too excited, here's the truth. There's no record of this happening, not from IBM, not from Google, not from Nature, not from any peer-reviewed journal, not from any credible science publication, anywhere. When you actually go looking for the original source of this claim, you find nothing solid. No press release, no research paper, no statement from either company's quantum computing division. What you find instead is a tangle of viral posts, recycled clips, and secondhand summaries that all seem to trace back to the same vague, unverified rumor. It is the kind of story that sounds compelling enough to share, but falls apart the moment you ask for evidence. So why does a claim like this spread so fast? Partly because quantum computing already feels like magic to most people. It involves words like superposition and entanglement, concepts that even physicists describe as strange and counterintuitive. When something already feels mysterious, it becomes incredibly easy to attach an even stranger story to it and have people believe it without question. Add in two of the most recognizable names in technology, IBM and Google, and a hint of multiverse theory, and you have the perfect recipe for a story that travels much faster than the truth ever could. Here is what actually happened, and honestly, the real story is fascinating enough on its own without any fabrication. Google's Willow chip is real. It was unveiled in December of 2024, and it represented a genuine milestone in quantum computing, one that researchers have been chasing for nearly 3 decades. To understand why Willow mattered, you need to understand the single biggest problem holding quantum computers back, which is errors. Quantum bits, or qubits, are incredibly fragile. Unlike the bits in your laptop or phone, which reliably hold a value of 0 or 1, qubits exist in a delicate quantum state that can be disturbed by almost anything. Heat, vibration, electromagnetic interference, even cosmic rays passing through the chip can knock a qubit out of its intended state. This is called decoherence, and it has been the single largest obstacle preventing quantum computers from becoming genuinely useful machines. For years, the conventional wisdom was grim. As you added more qubits to a quantum processor to make it more powerful, you also added more opportunities for errors to creep in. More qubits meant more noise, and more noise meant the entire calculation could become unreliable. It was like trying to build a taller and taller tower out of blocks that wobble more the higher you stack them. Scientists knew that if quantum computing was ever going to scale up to something genuinely transformative, this relationship between qubit count and error rate needed to flip. Adding more qubits needed to make the system more reliable, not less. That flip is called crossing the error correction threshold, and it was first theorized back in 1995. For decades, it remained mostly theoretical, a target on the horizon that nobody had actually reached in a working system. Then, in December 2024, Google's team announced that their Willow chip had done it. As they scaled up the number of physical qubits used to create something called a logical qubit, which is essentially a more stable, error-protected unit built from many physical qubits working together, the error rate did not increase. It dropped, and it dropped exponentially. Every time they doubled the number of physical qubits in the logical qubit, the error rate was cut roughly in half. This was the first experimental proof that the long-theorized below-threshold regime was achievable in a real machine, and it sent ripples through the entire scientific community. To make Willow's achievement even more tangible, Google ran a benchmark test on the chip, a type of calculation called random circuit sampling. This benchmark is specifically designed to be something that classical computers find almost impossible to simulate efficiently, while a working quantum computer can handle it naturally. Willow completed this benchmark task in under 5 minutes. According to Google's estimates, the very same task would have taken one of the world's fastest classical supercomputers an almost incomprehensible length of time, somewhere in the neighborhood of 10 septillion years. If you tried to write that number out fully, it would be a 10 followed by 24 zeros, a number so large it dwarfs the current age of the universe many times over. Now, it is worth pausing here, because numbers like that tend to generate their own kind of hype, and history has taught us to be careful with benchmark claims in quantum computing. Back in 2019, Google made a similar claim with an earlier chip called Sycamore, stating it had achieved what they called quantum supremacy by completing a task that would take classical supercomputers roughly 10,000 years. IBM, which has historically positioned itself as the more cautious, skeptical voice in the quantum computing world, pushed back. IBM researchers found a way to simulate the same task using improved classical algorithms and ample storage, completing it not in 10,000 years, but in a matter of 2 to 3 days on a powerful supercomputer. That dramatically narrowed the gap between quantum and classical performance, though it did not eliminate Google's advantage entirely. It was a useful reminder that headline numbers in this field often come with asterisks, and that the classical computing world tends to find clever shortcuts once it is properly motivated. With Willow, Google seemed to have learned from that experience. This time, the team explicitly tested multiple classical simulation strategies before publishing their results, trying to anticipate exactly the kind of counterargument IBM had raised in 2019. They wanted to identify what they called fundamental obstacles that classical algorithms genuinely struggle with, rather than simply claiming a speed record and hoping nobody could catch up. Whether that fully holds up over time remains to be seen, since clever classical algorithms have a habit of surprising everyone. But it shows that the rivalry between these companies has matured into something more rigorous and more carefully scrutinized than it was 5 years ago. Then, in October of 2025, Google pushed things even further with something called quantum echoes. This wasn't just another error correction milestone. It was framed as the first ever verifiable quantum advantage demonstrated on real hardware, a phrase that carries a very specific and important meaning in this field. Quantum advantage means a quantum computer doing something faster or better than the best available classical methods. Verifiable means that the result is not just claimed, but can actually be checked and confirmed as correct. That distinction matters enormously because one of the long-standing criticisms of quantum computing demonstrations has been that even when a quantum machine produces an answer, there is often no independent way to verify whether that answer is actually right, especially for problems so complex that no classical computer can check the work. Quantum echoes used an algorithm based on something called the out-of-order time correlator, often shortened to OTOC. Think of it like this. Imagine you send a tiny disturbance rippling through a complicated system, let it bounce around and interact with everything inside that system, and then you reverse the process, sending the disturbance backward through time, essentially asking the system to undo itself. By comparing what comes back to what you originally sent in, you can learn an enormous amount about how information spreads and scrambles within complex quantum systems. This kind of analysis has applications that go far beyond computer science. It connects to questions about how black holes scramble information, how magnetic materials behave, and how molecules are structured. In Google's published results, which appeared in the journal Nature, this quantum echoes algorithm ran roughly 13,000 times faster on the Willow chip than the best available classical algorithm running on one of the most powerful supercomputers currently in existence. To put that into perspective with real numbers, a single piece of data from one part of the experiment, involving 65 qubits and deep, complex random circuits, was estimated to take 3.2 years to compute classically on a machine called Frontier, widely considered one of the fastest supercomputers on the planet. Willow produced an entire series of equivalent data points in a matter of minutes. Google's team also reported testing the problem against 9 different classical algorithms, and found that every single one of them struggled to come anywhere close to replicating the results in any reasonable amount of time. But the truly remarkable part of this story is not just the speed, it is what they actually did with it. Working in partnership with researchers at UC Berkeley, Google's team applied the quantum echoes algorithm to a real, practical scientific problem, studying the molecular geometry of actual molecules. They tested it on 2 different molecules, one containing 15 atoms and another containing 28 atoms. The goal was to see whether this quantum technique could accurately map out the physical structure of these molecules, essentially functioning as an extremely precise molecular ruler. They compared their quantum-derived results against traditional nuclear magnetic resonance, or NMR, which has been one of the gold standard techniques chemists and biologists use to study molecular structure for decades. The quantum results matched the established NMR data closely, which was already a meaningful validation. But beyond simply matching, the quantum approach also revealed additional structural information that traditional NMR methods were not able to capture on their own. This is a genuinely big deal, and it deserves real, unembellished excitement rather than fabricated stories about parallel dimensions. If this technique can be refined and scaled up, it opens the door to using quantum computers as practical tools in drug discovery, helping researchers understand exactly how a potential medicine binds to its target molecule inside the body. It could also become valuable in materials science, helping engineers understand the molecular structure of new materials, whether that is next-generation batteries, advanced polymers, or even the very materials used to build better qubits in future quantum chips, creating a kind of feedback loop where quantum computers help design better quantum computers. Now let's talk about IBM, because IBM's actual role in this story is just as interesting as Google's, even though it has nothing to do with detecting any mysterious shared signal from thousands of miles away. IBM has taken a notably different path through the quantum computing race compared to Google. Where Google has often grabbed headlines with dramatic single benchmark announcements, IBM has positioned itself as the company building infrastructure for sustained, practical, long-term progress. Back in 2016, IBM made a decision that quietly reshaped the entire field when it opened cloud access to its quantum hardware through what it called the IBM Quantum Experience. For the first time, researchers, students, and developers anywhere in the world could log in through a browser and actually run programs on real quantum hardware, rather than reading about quantum computing only in theoretical papers. This single decision dramatically broadened participation in the field, pulling it out of a small circle of elite, heavily funded research labs and putting quantum tools into the hands of a much wider community of curious minds. IBM has continued building on that foundation ever since, focusing heavily on gate fidelity, meaning the accuracy and reliability of the basic quantum operations performed on its chips, and on cloud accessibility through its Qiskit software platform, which has become one of the most widely used tools for writing and running quantum programs. In May of 2022, IBM laid out an ambitious roadmap announcing plans to deliver a processor with more than 4,000 qubits by 2025. Built using a modular approach that combines multiple clusters of smaller quantum processors working together, all coordinated through what they call Qiskit runtime. The thinking behind this strategy was that raw qubit count alone does not solve quantum computing's problems. You also need an intelligent software layer capable of managing errors, distributing computational work between quantum and classical systems, and making the entire process accessible enough that programmers without a physics doctorate can actually use it. More recently, in November of 2025, IBM unveiled new hardware called the Loon processor alongside something called the Nighthawk chip, both representing the next steps in IBM's effort to build processors capable of handling increasingly complex calculations. IBM has described its broader strategy as moving the field from what is sometimes called quantum utility, where near-term, imperfect quantum devices already produce results of genuine scientific value even before reaching full error correction, toward eventual fault-tolerant quantum computing, which IBM has stated it expects to achieve by the end of this decade. So while it makes for a much less viral headline, the honest version of this story is that IBM and Google are not mysteriously detecting each other's signals across continents. They are running parallel, competing, and sometimes complementary research programs, each pursuing fault-tolerant quantum computing through different architectural choices and different philosophies about how to get there. Google has leaned heavily into headline-grabbing benchmark demonstrations that showcase raw quantum advantage. IBM has leaned into infrastructure, accessibility, and a methodical, incremental roadmap. Both approaches are necessary for this technology to actually mature into something useful, and the healthy skepticism each company shows toward the other's claims, like IBM's pushback against Google's 2019 supremacy announcement, actually makes the field stronger and more scientifically rigorous over time. It is also worth understanding why this kind of misinformation tends to specifically target quantum computing rather than other areas of technology. Quantum mechanics itself is famously strange, even to professional physicists. Concepts like superposition, where a particle can exist in multiple states simultaneously until measured, or entanglement, where two particles become linked in such a way that measuring one instantly affects the other regardless of the distance between them, sound almost mystical when described in plain language. Even brilliant physicists have spent entire careers arguing about how to properly interpret what quantum mechanics actually means at a fundamental level. Albert Einstein himself was famously uncomfortable with some of its implications, referring to quantum entanglement as spooky action at a distance. When a field already sits this close to the edge of common intuition, it becomes incredibly easy for misinformation to slip in, because the line between genuinely strange real physics and pure fabricated nonsense is harder for the average person to identify. A claim about a quantum computer somehow detecting a signal from a parallel universe does not sound that much stranger than some of the real peer-reviewed interpretations of quantum mechanics that serious physicists genuinely debate. That is precisely what makes a false claim like this so effective and so dangerous. It borrows credibility from real science while offering none of the actual evidence, peer review, or reproducibility that real science requires. This opacity, whatever its technical justifications, has fed the suspicion that the company is managing perception as much as reporting results. There is one more dimension to this story that rarely gets the attention it deserves. The question of what happens to the scientific and engineering talent involved if Microsoft's approach ultimately fails. Hundreds of researchers have spent years, in some cases the majority of their careers, on topological quantum computing. If the field concludes definitively that Majorana-based topological qubits cannot be built with current or near-future materials and techniques, the reallocation of that talent would represent one of the most significant redirections of scientific human capital in recent technological history. The people who built the Sydney lab, who designed the fabrication processes in Denmark, who derived the theoretical frameworks underpinning the topological gap protocol, they carry knowledge and skills that do not simply disappear. But the question of how that talent finds productive application in a world that has moved on from topological qubits is not a small one. It would be a loss, measured not just in money, but in scientific years, in intellectual opportunity cost, in the questions that were not asked because this particular question consumed the oxygen. None of this makes Microsoft wrong. It is worth saying clearly because the cumulative weight of the skepticism and the history of retractions can make it easy to assume the outcome is already clear. It is not. The physics of topological phases is genuinely rich and genuinely difficult. The possibility that Microsoft's experimental results are closer to correct than the critics believe is real. The possibility that replacing aluminum with lead in the device stack has genuinely moved the system into a more robustly topological regime, not merely a longer-lived trivial state, cannot be ruled out on the current evidence. If Majorana 2 is followed in 2027 or 2028 by a demonstration of topological qubit braiding, by a running quantum algorithm on a topological processor, by independent replication of the key results by groups who had no prior stake in the outcome, then the story will look very different in retrospect. Microsoft will look like the company that stayed on the right path when the critics were loudest and won. But right now, today, on June 19th, 2026, what we have is a company that quietly closed a major lab and reopened something far larger. A chip that claims 1,000 times better performance, built on physics that the scientific community has not yet validated. A timeline compressed to 2029 by an agentic AI system helping design materials. A partnership with Atom Computing. A facility in Denmark that is the largest quantum site Microsoft has ever built. A new center at the University of Maryland. And critics who say none of it changes the fundamental unanswered question at the heart of the enterprise. The lab is open. The investment is real. The controversy is unresolved. And the particle at the center of it all, the Majorana fermion, predicted by a man who disappeared into thin air in 1938, remains exactly as elusive and tantalizing as it was when Microsoft first decided to go looking for it. What they restarted may well be more consequential than why they ever closed. The question is whether the consequence will be triumph or warning. And that answer is still being written, one 22nd qubit lifetime at a time, in a clean room in Denmark where the temperature never rises above a fraction of a degree above the coldest cold that physics allows. The race for quantum supremacy is not a single sprint. It is a long, brutal, technically unforgiving marathon being run simultaneously by dozens of organizations across the world, and Microsoft, for all the controversy surrounding its approach, is not running it slowly. They are accelerating. Whether that acceleration is carrying them toward the finish line or away from it, only the physics will decide. And physics, unlike a press release, has never been known to lie.